And thanks to the MacArthur Neuroscience and Law Network for introducing me to a lot of the people, some of which I've done this work with. This is work I did. This is going to be a very narrow slice compared to the big issues that you've heard about. Not because I'm particularly modest about what I do, but because what I do warrants narrowness. I mean, the kinds of questions I ask warrant saying narrow things, and so I'm not going to make any overarching statements about culpability or assigning valence to it. But I think you'll see the significance. I did this. I conceived of this with Gideon Yaffe, who is also in the Neuroscience and Law Network, MacArthur, and did this with colleagues at Baylor College of Medicine. I'm in transit now to Virginia Tech and University College London. For some reason, this is not. There we go. Okay, and that's the question. That was the motivating question. Should the law subjectivize the reasonable person standard with respect to addiction? Okay, I will not answer that question today. But I will note for those, lots of professionals in the audience, that sometimes the law holds persons to lower standards. And the typical case, and we heard this this morning from the judge, that low IQ, or so-called mental retardation, is a feature of that. So could this person be held accountable for X, Y, and Z? Mental retardation is a state for which you have a quantitative measure. Things are mitigated or subjectivized according to that. We thought that addiction held. Do I get control of this with this? Okay. We thought that drug addicts posed an interesting test case. I don't. Sorry.
If that's not working, we'll try mine. See if that one works. It should work.
Oh, there we go. Thank you. Ran off with it, did you?
No, that's mine. That's mine. I'm not a thief.
This psychopath thing doesn't insulate you, Okay, first of all, drugs of abuse. Every drug of abuse that you can name works on systems in your brain, and these are networks of systems that are involved in risk and reward processing. That's a fact. Won't go into the details of that. I'm an expert in some pieces of that. Secondly, the changes that occur there are thought to at least in part underlie some of the decision-making deficits that drug addicts have. If you're called a drug addict, you by definition have a decision-making deficit. You're trading parts of your life for putting white powder up your nose. That's not a good decision. I think we could all decide quite narrowly on what we think a good decision is in that context. And thirdly, and I'd like to use this moment to hover a bit, that is, we need precise assays of the nature and severity of the neural changes and the consequences that you can expect from that behaviorally. And by that, I don't mean the consequences just doing 12 people. I mean any kind of what you would expect out of any kind of biological assay. That is, if you have this range of changes in these systems, then what are the range of behavioral consequences? It's biology. No matter how hard we work on this problem, no matter how many, let's say, hundreds of thousands of people we study, it's going to be a distribution. There's not going to be a one-size-fits-all answer, and there's certainly not a one-size-fits-all answer for addicts. The other thing is, and this has come up as I've listened to people talk about whether neuroscience is going to be important. Are we just finger-painting ideas in psychology and or folk psychology onto brain activations or whatnot? In large part, we are right now. In large part, and then how do we translate that into a kind of circuitese? This person's amygdala went up and down on these things. Whenever that happens, they tend to not be able to fear condition, or they're not be able to control themselves and whatnot. The big gap in my mind, and I won't belabor this, but the big gap in my mind is this in-between lexicon that we completely lack, and that is what are mental states? What is the software space, if you will, in which we think? For lack of a better term, we have no descriptions here at all, almost none. So what do we do, really? What do people like me do that know a lot about the neurobiology? We go to parts of psychology where these things are operationalized in reasonable ways. They have mechanisms where these psychological variables relate to one another, and we try to sort of find a connection between the two. If you're going to do that with a computer, and you were going to show in this computer, when this computer is running this cooling system for the nuclear power station over here, it's using this part of memory a lot. And look at that, this part of memory is really hot. And what happens when we cut that part of memory out? Does that software work anymore? We can't answer that unless you know what the software looks like. And so the big gap here isn't in the brain science, and the big gap isn't really on the edge of psychology. It's somewhere in between, sort of extending psychology, if you will, to real mental models. And there are no mental models. There's no sort of even bad working model of the brain. Okay, with that as a disclaimer, I think that's a cry for where it is that there's a big gap. These other structural issues relating to a lot of these things, I can't really speak to because they're big and they're really complex. Okay, but we already have candidate neural systems that participate in valuation and choice. So, and they're identified. They're at least in part involve dopamine neurons identified in your midbrain. These are the neurons that are hijacked by drugs of abuse. These are the neurons that when you lose them, you have Parkinson's disease. They're intimately related to motivated learning. If you don't think so, just take away your dopamine neurons and see how motivated you are to learn. They emit error signals that guide valuation and choice. These error signals are extracted now from fairly sophisticated computational models. Okay, so they're not just psychological ideas, they're computational models about how adaptive agents should use feedback signals to go navigating a world. And what's happened in recent years is that these error signals have been mapped onto very detailed electrophysiology and basically neuroanatomy in the brain in primates and rodents. So it gives us a really good test condition to take what we know here, these very detailed descriptions, map them onto measurements already done in dopamine neurons, and extend this to human beings. Okay. This is just a diagram showing at the top, this is from Scientific American and flipped over for your viewing pleasure. These are the dopamine neurons in your midbrain. This is your midbrain. There are about 25,000 neurons per side in a human, 25 to 30,000. They project to various regions of your brain. They make the neurotransmitter dopamine. They project to a region called the striatum, which is here. If you draw your attention back down here, this circle here is where I'm pointing to. I have these analogous circles. This is the so-called ventral medial prefrontal cortex, a region known to be involved in valuation, and the valuation that goes on there, it requires an intact ventral medial prefrontal cortex, and it also requires dopamine. It is involved. These systems are involved, and again, this is neuroscience light. I'm not giving you details or equations, but they're involved in valuation and choice related to everything from reward predicting cues to abstract mental states. I put a few reward predicting cues up here that everybody knows. I don't know if the British that are in the audience here know Krispy Kreme donuts, but these are more diabolical than cocaine and heroin. And you always eat one more than you decided to eat. Your sort of satiety function goes up slowly. You eat that last one, you go past threshold, and you're sick for an hour. Okay, so they're broadly involved in something to do with the rest of your brain talks to them. Of course, there's just a small number of neurons here. They're not doing all these things. They're being fed a lot of information. They're computing things, and they're handing it out. We understand some parts of those computations. This region, the ventral medial prefrontal cortex here, and I've given you a glass brain diagram here showing you different kinds of things, give what are called parametric valuation responses. So across a broad range of evaluations that I could give you. Beautiful people, funny jokes, we have sports cars, odors, beautiful paintings, whether you preferred Coke and Pepsi, facial attractiveness, brand preference or drinks, pleasant, it goes on and on and on and on and on. So the enormous number of experiments have shown that what you can see in this region of the brain is you'll get parametric responses to valuing things. So in Phineas Gage, Kent Keel showed you earlier, when he lost that region of his brain, he lost a fundamental piece of the way he makes decisions and the way he controls his behavior. Okay. What I'm going to focus on is, again, something narrower, which are the error signals that are generated at the level of dopamine neurons, and which would show up in an imaging experiment at the places to which these neurons send their connections, which is here in the striatum and here in the ventral medial prefrontal cortex. Okay? Our strategy was to track two kinds of errors that we know are generated and can be seen at the level of these neurons. The first is what we call reward prediction errors. These are like expectation errors. Your brain forms an expectation about how much juice it expects to get, and it compares this to how much juice you actually get, and it forms these expectations through time, tick, 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 into the future, into the nearby future. We'll call those errors based on actual experience. And secondly, counterfactual experiences form errors at this locus too. I call these fictional errors, and this is the difference between not what you got and what you expected to get, but what you might have gotten had you chosen differently, and what you actually got. Okay, two separate kinds of error signals. And when we go looking for these things in the brain, we're not looking just to activate an area. We do paradigms where you're making decisions for, let's say, 30 minutes, and we compute through the differential equations that capture the performance of the system. We compute what it would look like through the whole way, and then we go fishing for this sort of complex time series. I'm not showing you any of that, of course. Okay. The inciting intuition was that people who are addicts, in some sense, can't act on fictional near-term predictions. In other words, the idea was that perhaps it could be that these fictional error signals that have been seen in primates and been seen in humans in experiments that we and others have done, future negative consequences can't intervene on their habit chasing right now. Okay? So maybe they're either missing these signals, maybe the signals are getting computed and somehow they're disconnected from behavior. Okay, here's the task. You sit in front of a screen. There's a market. It starts at some point, played out, same point every time. They play 20 markets. This is the price here. This is time on the x-axis. You have a portfolio, a total amount that you have. You start with $100, and people get paid in cash. You decide whether your confidence in the market, and you adjust your bet between 0% and 100%. You pick some level. This shows your confidence about what you expect the market to do. Okay. Then the market either fluctuates up, in which case, as I've noted right here, at that point, and only at that point in time, all the bets bigger than the bet that you made were better. Okay? So it could have been different had the bet been higher. We compute a difference between the best bet you might have made, 100%, and your actual bet, and that becomes your fictional area, or something proportional that does. Or the market might have fluctuated down, in which case you lose money, and at that point in time, it would have been better to cash out to zero. Okay? Notice for those of you that know about markets, you can't short the market. You can't bet that the market's going to go down. People didn't understand that. So this is sort of half an experiment. Okay? We track this in people's brains and in their behavior, and this is a result of the behavioral analysis. The question is, do fictive errors guide your behavior? There are two main variables that guide your next bet. The first is, how well the market's doing, and the second is the fictive error. Okay, not what you actually got. That's an interesting thing. So if I bet 40%, market fluctuates up, I make money. Well, what governs my next choice? It's not whether I made money and I'm feeling happy about that. It's the degree to which I could have made more. It's this kind of almostness parameter. And people that are gambling addicts describe things that way. So this is an interesting sort of regret-like feature to this signal. Anyway, as you can see here, low, medium, and high fictive error. Big fictive error explains something like 80% of the variance in your next bet on this game. Okay? Nope, there's no incentive here. And even though you're playing a market, nobody makes on average more money than anybody else. Okay, so I haven't put an incentive structure on top of it on average. Here's what happens when you do healthy people on the task. You can ask for this dynamic. Show me the place in the brain that tracks the dynamic of the fictive error for a half an hour through the whole task. And one answer is you see it in a region called the dorsal striatum. It's tracking it up and down throughout the whole task. And you see it in their behavior. In other words, you do behavioral regressions and you ask, how does this parameter control what they do next? Then we took 40 cocaine addicts. We're still in the middle of this. We did this with our colleagues at the VA hospital. They recruit non-treatment seeking cocaine addicts. And we have them, I'm showing you just the results when they're off cocaine. So these are this is from 39 subjects. And we're doing the same analysis we did on the 39 matched controls. And you see nothing here. The reason I don't put a hard conclusion here, and I do put a yes there, is that, and I think Owen Jones mentioned the whole base rate phenomena. We have, in functional imaging, the one thing we really don't know is false negative rate. Every time I don't see something, how significant is that? And the answer is, I'm mute on it. I'm just not seeing it, and I'm not seeing it. In other words, I don't have a good estimate yet of the false negative rate. So I don't know my likelihood of actually seeing this, and nobody really has a good method for this yet. This is something the field struggles with. On the other hand, their behavior is their behavior. They're absolutely guided by the fictive error, like healthy people when they're off cocaine. We take the same people and have them come in hot. When they come in hot, they get sent over to us. We do the same experiment. This is on a hot cohort. This is not within subject. Two things to note. Now, all of a sudden, you can see the fictive error signal showing up as a neural response. Okay? Very, very strong. I'm not showing you p-values and false discovery rate corrections and all. But there's no impact at all on their behavior. They're basically behaving randomly. And their stickiness on their last bet changes too. Okay, so 0 minutes. Perfect. The two summary points I'd like to make, and I don't usually make summary slides, actually. The first is these kinds of experiments are addressing, is there something different in these addicts' brains once they become an addict, whether or not you want to blame them for not for that. And the answer is, well, probably. It's profoundly different in the way they behave and are affected by the drug when they take it. But this is what I want to emphasize here. And this requires this. That is, we need to shift from sort of categorical assessments. Well, were you addicted or not? Were you responsible for your behavior or not? I just don't think the answer is ever going to look like that. No matter whether brain imaging goes down and looks at every neurotransmitter in the brain as an imaging at 10 microns or whatnot. That's just not the nature of the question. That's like insisting on what color is 3 o'clock. I really think it's the wrong way to ask the question. Lastly, we need normative data. We just don't know how we don't have data distributions from thousands and thousands of healthy people on almost any task, other than IQ and whatever it is that ETS gives you to go to college and whatnot. What experiment has ever been done on 500,000 or 1 million people? And the answer is none. You go down the hall from me at my former institution, Baylor College of Medicine. I got 15 seconds. I'm done in 15 seconds. And there's a Drosophila geneticist there that studies behavior and the genetic basis of behavior. They will screen 1 million individuals to find a few mutants of, these are fruit flies, right? These are stupid animals, the ones that sort of go down and turn left at the T maze instead of right, and so they get the dead apple instead of the alcohol or something, right? And they find mutants of that, or the ones that when they're standing there and they heat them up, they can still stand there and beat their wings. 1 million. They'll screen 1 million individuals. Surely our cognition is at least as variable as Drosophila. And so that's basically a plea for being a little more conditioned to collect the data, let the data fall where it may. Okay. Sorry.